We have two groups in robotics detail design this semester. This is going to be the first group presenting. They're going to talk about their robotic boat project. So I'm going to turn this over to Logan, and we'll get started.
Thank you. So we are Narwhal Robotics. My name is Logan McDonald. I'm the team lead. Right over there we have Yanni Todd. Right next to her we have Sylvia Villegas. And right next to her we have Lasha Atkin. And today we're going to talk about our detailed design project. So according to a 2015 report by the Arizona Department of Environmental Quality, Watson Lake was ranked the most eutrophic lake in Arizona. What this means is that the water pollution level is so high that algae grows excessively. So this has become a problem for recreational activities such as boating or fishing, and this is why we created Narwhal, to help solve this problem. And Narwhal stands for Navigating Autonomous Robot, which handles water. So in this presentation, we're going to go over the requirements of our design, the physical, electrical, and software portions of our design, and then we'll talk about the budget, and we'll conclude it all. So the requirements for our design, we broke our requirements down into 5 subsystems: the body subsystem, the waste storage subsystem, the propulsion subsystem, and the electrical and software subsystem. So for the body subsystem, we wanted our robot to be water resistant as well as rust resistant, since it's going to be operating on the lake. We also wanted it to be eco-friendly and safe. And we also wanted it to be stable while navigating and also be able to float on the water. For the waste storage and propulsion subsystems, we have 3 requirements total. We want the waste storage subsystem to collect and filter waste from the water. And we also want it to be able to dispose of that waste easily and effectively. For the propulsion system, we only have 1 requirement, and that is to be able to navigate at a reasonable speed. For the electrical subsystem, we want our electronics to have simplistic circuitry. We also want our battery to have a long battery life. And all of our components, minus the motors, we want them to be rated as low power consumption components. And also we want to know when the battery is running low. And finally, for the software requirements, we have 3. We want the robot to maintain a reasonable distance between the shoreline and any sensed obstacles at all times. And we also want it to be autonomous. And finally, we want it to have basic localization capabilities. And now I'm going to pass it over to Yanni, and she's going to talk about the physical design.
Thank you, Logan. Can you guys hear me well, or do you guys need me to use a microphone? Good. As part of the physical design, I'm going to be going over the main features of the robot as well as the manufacturing process. In addition to that, I'm going to be going over the specifications for 3 main subsystems of the robot, and as well as how the design met those specifications if it did. And I'm going to wrap it up with a expenditure list, also known as parts list. So let's start. For those of you who are not fortunate enough to be sitting at the front, you're looking at an isometric view of the robot at the screen. The first feature we'd like to point out is a set of floats made out of styrofoam. They are located right here. These are the front floats. Over here, there are the center floats, and also some side floats. In addition to the side floats, the second feature is the battery box. Right here, the golden box you see right here. It's also made out of styrofoam, and it's covered in fiberglass layers. It was intended for a bigger box, but our design changed. But we were still able to find a 12-volt, 18 amp-hour battery lead acid that still satisfied our consumption we kept the boxes and it was really functional. The third feature is this collection box in the center. It does not fall down because the lip of the box sits on the top of the front floats. And also just to secure it in place, we added some extra bungee cords to secure it to the PVC frame. It was not falling already, but we just wanted to make it extra safe. The box is just plastic. We cut out a hole right here, and there's also some mesh screen at the bottom of the box and also in the back, so that when the volume of water is coming into the box, the water can still filter out back to the lake. The next couple features are covered in the next slide. We have these motor boxes, if you can see them. They're custom made, they're made out of HDPE. HDPE came in this sort of material. Those took way longer to manufacture than we expected, and we learned from that. So when we were ready to design the electronic boxes, we decided to just go with off-the-shelf commercial boxes. Currently, we're only using this smaller box. We were able to fit all our electronics there. And next, we have the paddle wheels right here. Those were 3D printed here at school. The design was made last semester, and we just used that. And I would say the main feature of a robot would be this water ramp. That's our main collection mechanism. At the bottom of the ramp, we drill a series of holes to allow us to adjust the water ramp if we needed to in the future. We secured it in place the first time, and it's actually just like this. And the nice thing, I don't know if you can see right here how the width reduces a little bit. That allows the water ramp to just sit very nicely inside the mouth of the box. And that's all for the design features of the robot. Now we're going to be talking about the manufacturing. So since most of the frame was made out of the styrofoam, we decided to just start building those parts. And as you can see, we cut out 1-to-1 scale pieces of the parts. We laid them on top of the styrofoam, and we cut those pieces out. We also had PVC pipes that we cut into sections, and we started to build the skeleton of the robot. And at the same time, we were 3D printing the paddle wheels. This didn't take very long, so it took a couple hours. Next were the HDPE boxes. That stands for high density polyethylene. We did everything we can to keep them together. Before we applied the fiberglass right here, we had to make sure we had as smooth of a surface as we could. So we fill in the gaps with Great Stuff expanding foam. We let it dry, we cut out the excess, and we sanded the surface as much as we could. And for the smaller areas, we just applied some spackling putty. And again, once that was done and that was dry, we sanded the surface again, and then we applied more styrofoam, the fiberglass layers. We then painted all the parts, and we assembled it together. This was the last improvement that we made physically to the robot. We noticed that once the frame was built and we were transporting it, it would just kind of fall apart. So Lash and Logan ended up adding some aluminum extra support around the motor boxes to secure it in place. And the last thing we did was to install the electronics on the robot. And once it was finished, it looked like this, just like that. Next, let's go over some specifications. There were three subsystems that I'll be going over. The first one is the body subsystem, and there's 6 requirements. The first one was that all seal boxes must be able to be waterproof up to 1 foot below the surface of the water, and that meant the requirement that the body subsystem must be water resistant. The way we tested this specification is by grabbing these motor boxes. We placed some paper towel inside them. We put them in water. We added some weights. We let them sit for about 15 minutes. Then we removed them from the water. We opened them, and we looked for any water presence. If there was a leak, we found the leak. We seal it again, and we repeat the process until all the boxes were completely waterproof. Therefore, this specification was met. The next two specifications were that the minimum radius had to be at least 1/16 of an inch, and also that the HDPE that I mentioned earlier should not be buried more than 5% over a course of a week. The way those two specifications met the requirement that the body subsystem should have an eco-friendly and safe design. The way we tested the first one was pretty simple. We just went on all the rounded surfaces and we recorded the radii, and the average was at least 3 times 1/16, so we were good. We passed that specification. The next specification, we tested it by grabbing this section of HDPE, we weighted it, we placed it in the water for about 10 days, and after 10 days we weighted again. And we noticed that the amount it reduced, it was almost negligible. That way we determined that that specification was met by the design. The next two specifications deal with the stability of the robot. And the corresponding requirement was that the body subsystem shall be able to navigate in a stable manner. The first specification was that the robot should be able to stay afloat when a mass of 50%, when a mass equivalent to 50% of the overall robot's mass is placed on the center of gravity. And the second specification was that the robot should not tilt to its side when a mass equivalent to 25% of the overall mass is placed on one side of the robot or on the other side. So the first specification was tested by first weighing the robot. It was about 8.5 pounds. So we found some weights that were about 2.2 pounds each, and we placed them on the center of the robot as close as we could to the center of mass. And we noticed that the robot was fairly stable. And then we went ahead and tested the next specification, and we only placed one of the weights on one side. It was still not tilting, it was still stable. We repeated the same process on the other side, and based on our results, we determined that those specifications were met by the design. Lastly, for the body subsystem, was that we should not collect more than 25 cubic inches of waste based on our overall dimensions. So the way this requirement met the specification of the waste storage subsystem shall effectively collect and filter waste from the lake. And the way we tested this specification was just by grabbing the collection box, measuring width, length, and height, calculating the average volume, and that came out to be about 450 cubic inches, and that was way less than the 2,500 that we had maxed out. So based on our design, that specification is being met. For the next subsystem, the waste storage subsystem, we only had 3 specifications that we were concerned about. One was being able to collect algae at least 2 inches from the surface, because back in October, when we went to the lake and we did we collected algae samples, we noticed that the algae tended to float not only on the surface, but also a little bit below the surface of the water. That's why we came up with 2 inches. We also wanted to collect algae at least 0.1 pounds of algae over a course of an hour, and we wanted to have a mesh size of at least 30 openings per inch. Those were our 3 specifications. All 3 of them met the requirement that the waste storage subsystem shall collect and filter algae effectively. So we tested the first specification. You see on your right, there's an image on the upper right-hand side. And we just had a ruler, and we took several measurements, and the average measurement was at least 2 inches. So that specification was met by the design. Next, the next specification was tested. We couldn't actually test it because we couldn't get the main program to run. So we don't actually know if we met that specification or not. And the third specification, it's pretty simple. We actually got the mesh size we needed, which is 30 openings per inch. They're actually much smaller ones. And for the last subsystem, the propulsion subsystem, we have only 2 requirements. That the robot should navigate at least at 1 mile per hour, but no more than 4 miles per hour. Those 2 specifications met the requirement that the robot shall be able to navigate at a reasonable speed. And the way we tested those specifications was by putting the robot in the lake, setting it to 100% duty cycle, and taking the average speed of the robot by using a difference equation of the distance and the time for a straight path. You can see the graph right here, the graph we use. And the values we obtained were experimentally an average of 0.32, 0.34 miles per hour, and from the GPS we got a 0.52 miles per hour. Based on these values, we know we did not meet the first specification because we were not able to run at least 1 mile per hour, but we do know that we meet the second specification because we did not exceed 5 miles per hour. And that concludes my section of the presentation. Now I'm going to hand it over to Sylvia, who's going to talk about the electrical design. Oh, never mind. Parts list. I forgot to read the slides. We spent about $265 on all the parts just for the physical building of the robot. And we actually got the sponsorship from Rose, so this would have been like $150. Thank you, Rose. Now I'm going to hand it over to Sylvia.
Thank you, Yanni. Can everybody hear me?
Yes.
Okay, good. So, along with the electrical design, I will be covering the block diagram, and all the electrical components that we used and their purpose, a schematic and our printed circuit board layout, the electrical specifications, and wrap it up with the electrical parts list. So this just shows an overview of our block diagram of our whole electrical design. So what we ended up using is just one 12-volt battery to power all of our components, since all of our components use less than 5 volts. So in order to give each component the proper voltage, we implemented 3 voltage regulators, 2 being powered at 5 volts and 1 at 3.3 volts. If you draw your attention over here, this is our 5-volt voltage regulator, which we only use to power our microcontroller just for safety purposes. Our other 5-volt regulator will be powering our compass, our GPS, and our digital servo. And lastly, our 3.3 will be powering our ultrasonic sensor and our motor driver. And I also included the type of signal that each component will be using to communicate with our microcontroller. For example, we have our compass communicate using an I2C signal, and our motor driver using a pulse width modulation, PWM, and so on. So first we have our ultrasonic sensor. This is essentially used for our robot to be able to avoid any obstacles as it's navigating in the lake. If it comes across one and a rock or something in the lake, our robot will be able to sense that and turn away from it. Next we have our digital servo, which is used to just control the angular and linear, just the angular position of our ultrasonic sensor. But we ended up not implementing this to our design since we were pressed for time and didn't have time to come up with the software. Next we have our GPS. Of course, and we not only want our robot to know where it is in the lake, but we also want our robot to know what areas in the lake to completely avoid, whether it be the shoreline or the ramp. Next we have our compass. This is essentially just so our robot knows what direction it's facing, and it actually had other interesting features such as a gyroscope, an accelerometer, and a barometric temperature sensors, which actually ended up giving us really good readings during the testing phase. And like I said before, we want our components to have the proper voltage. We added in 3 voltage regulators, 2 5-volt and 1 3.3. So we also used a motor driver. Since we know that our microcontroller can't directly control the speed of our motors, our motor driver will teach us that through using a PWM signal to control the speed of our motors. So we use 2 gear motors, one for helping controlling the speed of our power wheels. lastly, we decided to use a Beagle Bone Black since our other detail team was using this Beagle Bone. We wanted to be able to work together in the software for all components. Sorry. Okay. So this is just an overview of our schematic showing each of our electrical components and their pinouts. This is just our printed circuit board design. If you guys aren't familiar with using EagleCAD, it has an interesting feature where glue just necessarily means that we're going to solder our components on the bottom, and any component that has a red layout or layer will be soldered from the top. So our electrical specifications, we wanted our battery to have a battery life for at least 3 hours while traveling or navigating 1 mile per hour. So this meets the requirement of having a long-lasting battery. And the way we tested this was we used this device, which essentially is able to decharge and charge our battery. So what we did is we ran the motors at full speed in the water and ended up drawing 1.63 amps. Our battery was indeed fully charged, and after 3 hours of discharging the battery at a constant rate of 1.6 amps, the voltage we tested the voltage across our battery terminals, and it actually gave us a reading of 11.25 volts. So that meets our requirement of having long-lasting battery. Our next specification is no custom-made circuit boards, which meets the requirement of having simplistic circuitry. We actually ended up printing our own circuit boards for each of our electrical components, so we did not meet that specification. Our electrical prices overall, we ended up just spending $264.82 for all of our electrical components. And now I'll hand it over to Logan, who will be covering the sector matrices.
Sylvia? Okay. So, can everybody hear me? So I'm going to talk about, before I pass it over to Lashin, I'm just going to talk about the software design. I want to talk about an essential component of our software, which are sector matrices. So this image on your right is an aerial photograph of Watson Lake with a grid overlaid on top of it. So a sector is essentially just a square area of set distance. And as you can see, this whole grid, essentially each one of those squares represents a sector. And a sector matrix is essentially a matrix of a bunch of sectors which represents a large area. In this case, this map right here. Okay, so the first sector matrix we use is the sector type matrix. This provides basic physical information about what each sector contains, what the area inside the sector contains. So focus your attention on this image on the right. And this is a visual representation of what the sector matrix might look like. So right here in the blue area, we have the open water sector type, which basically is just inside the lake. There's no obvious obstacles around. It's free to run as fast as it can. On the edges, along the shoreline, we have a boundary sector, and that is areas where the robot does not need to go, such as land, and also areas where the robot should avoid. Right next to it, we have the boundary border, and that just borders the boundary, and it tells the robot that it is approaching the boundary, and it needs to perform certain actions to avoid it. This little blue or cyan sector right here is the home sector. There's only one home sector in this whole map, and that is essentially where the robot goes when it is to be picked up when we collect it. And finally, the caution sector, which is this yellow area, just tells the robot that it needs to slow down, can't go full speed, and be more cautious. And this is for areas where there's higher traffic, such as around the boat ramp, where people are fishing or unloading their boat. And our second and final sector matrix is the return home angle matrix. So what this matrix basically does for the robot is that when the robot reads this matrix and is trying to get back to the home sector, all it needs to do is orientate itself in the direction that is read from the sector or from the return home angle matrix. And by doing so, it doesn't need to compute. It doesn't need to do any heavy computations to figure out how to get home. It just reads the matrix, goes forward, and it also orientates it as it's going. So, as you can see, no matter where the robot starts, it can always get back home by following essentially the arrows, orientating itself as it's going forward. And now I'm going to pass it over to Lashin. He's going to talk about the rest of this.
So next following slides will cover modes of operation, the software design, the flowchart of algorithm used, and software specifications of our modes of operation. We initially implemented 7 modes of operation for our robot. As you can see in this figure, mode 1 is a move forward, mode 2, turn away from boundary, mode 3, return home, mode 4, authorized movement, mode 5, turn the random angle, 6, avoid obstacle, and 7, stop problem. We ended up not using the vectorized movement and turn random angle functions because not enough time to do. So software design for our robot is simply starting the mission of the robot and initializing all the variables before the main loop. In main loop, the start acquires data from GPS, from compass, and from ultrasonic sensor, and then it goes to mode selection, and depending on what mode is the robot in, the controller updates, and it goes to the main loop again. So move forward function starts by checking the sector type, and if it's open water, the robot moves forward at maximum speed around, and it executes the program. And it executes the mode. Otherwise, if it's ocean dome, it moves forward at 50% of full speed and executes the mode. Turning away from boundary function, first analyzes surrounding sectors and determines the best sector to move to. After that, looks at the current sector. If it's open or caution zone, it switches to mode 1, moving forward function, and executes the mode. Otherwise, it goes toward target sector and executes it. Move free return to home function starts by reading return home angle for current sector and moves forward and turns to the face return angle, and it looks what's the current sector. If it's home sector zone, it stops the motor and hibernates and executes the mode. Otherwise, it just leaves the home. Obstacle avoidance function is the most interesting that we will implement in our design. It starts by collecting ultrasonic data within 180 degrees range, and after that, analyzing ultrasonic data collected, and it sees if the obstacle detected, then it finds optimal angle, turn to face optimal angle, and move towards the set time, and switch to mode 7, which is stop the robot function. If it's false, switch to mode 1 and execute the program. concept is starts by running models in reverse based on speed, and looks if speed less than set speed, it's switched to mode 6, which obstacle avoidance function, and it leaves a mode, otherwise it executes that mode. So the controller we used in our design is based on two types. The first one is constant linear speed, and the second one is linear angular speeds using those equations. Software design specifications were divided by 4, which is a robot must not go to the water that is less than 4 feet deep, and robot must keep the distance of at least 20 feet away from the shore while collecting algae. The robot must be able to operate 75% autonomously, and it should go back to home sector 30 minutes of operating live feed. We were not able to meet the specifications simply because our robot was not fully equipped. And here I'll pass to Logan.
So I'm going to go over the last two specifications that we had, and then talk about the budget, and finally just conclude everything. So this specification, we wanted to make sure that the battery, that the user would be able to remove the battery in at least 10 minutes with all the tools present, in this case, a screwdriver. And as you can see, this is the process of removing. You remove the tape, take the lid off, and unscrew the screwdriver. And we did this 3 times with 3 different people, and on average it took only 1 minute, about 1 minute to, which in this case it passes the specifications. So the other specification that we had is that the robot, or a person must be able to get the robot and take out the collection box within 15 minutes of it arriving at the boat. And this meets the requirement that disposing of the waste is dispose of waste effectively. So when we did this experiment, it took about 3 minutes and 38 seconds to perform this task. And basically what we did is once the robot was at the boat ramp, we had a fishing line, and we hooked the fishing line onto the robot. And from there we could drag it to the boat ramp, and from there we can easily just take out, take off these 2 bungee cords, and the box simply slides out. So we met this specification. Finally, the budget. Between the mechanical parts and electronics, our total spending cost was $530.36, which was sadly $30.36 over our allowable budget, but we made it. So in conclusion, Narwhal Robotics, our whole team, has learned several different things over the course of this semester and prelim, which was last semester. We learned gained a good idea of the complete engineering process from start to finish, from prelim to writing. We learned how to create PCBs, and also we learned how to write Python on a Linux-based system, how to debug. So if we could start over, there's a couple or several things I guess you could say that we would do differently. First, well, we would spend more time, or less time manufacturing and more time developing the electronics and the software. And second, we would, instead of custom making these motor boxes from scratch, essentially, we would probably just 3D print them, since it turned out that that took a long time to finish up and actually get sealed. And finally, we probably want to create the PCB earlier in the semester, as well as, while that's being created, test our robot with the breadboard test the software correctly in the meantime while that's being. Finally, we would like to acknowledge all the professors and that helped us with this project: Dr. Eisenberg, Dr. Davis, Dr. Centellini, and also Jim. He just left. And also, we'd like to thank Lowe's for their sponsorship, which was 50% off everything that we needed for our project. Question?
Okay. Hey guys, great job. I'm Jeff Jansen. I work for Honeywell Aerospace in Phoenix. Great job on your project. It looks like you got a lot of good hands-on experience. Jimmy Johnson would probably say put Lowe's on the side of the robot. So that big money sponsorship that they gave you. So. Hey, a couple of questions. Could you go to page 7? Okay, and this is really around your initial presentation of your requirements. I'll just pick one. So reasonable navigation speed. All of us engineers love to see the numbers and the variable data. So I think later on in the presentation you said 1 to 4. Okay, so where you have measurable requirements, criteria in terms of we meet or we don't meet, make sure you put those things as much as possible in the upfront so everybody's going up and you know kind of what range you're looking at. Now later on in the presentation you did a good job saying it was 1 and we were at less than 1, right? So we didn't need that. Or you did. Okay, but try to quantify that up front as much as possible. Okay? Let's see. Another question would be, let's imagine that your robot is out doing a mission and the powered subsystem fails. Who's the best one? And my actual question is, what do you think about failure modes of your robot, and what types of things would you think about in terms of maybe designing redundancy into the system?
So first of all, with prevent the failure, it's safe. The power subsystem will be battery low in 30 minutes of life remaining and go back to home.
You have a control, your control algorithm says at a certain power level or a certain time or both?
So yeah, basically what we're doing is we're reading the voltage. We have a voltage divider in our circuit, so it drops down the voltage to a set amount. We know how much it drops, so we read it off the ADC on the microcontroller, and then we convert it back up to the amount that the batteries will outputting. And from there we can determine with precision what level of the battery.
Okay. And that's just an example. On an autonomous vehicle, you want to have redundancy design in the system. So in reality, you would probably use a higher power density battery, as you wouldn't have too much weight, and then have backup as an example. So think about that on autonomous systems in terms of, and depending how critical it is, how much levels of redundancy and what the design implications are. Let's see. When in your mission, as you could be collecting algae in your computer, would you also be anticipating accumulating water in there?
So
And do you think there would be a problem?
into the collection box.
Yeah.
So basically,
Can we just like remove it?
Yeah, sure.
so we have 2 screens, one on the bottom and one on the side. So as it's moving forward in the water, the water passes through.
Your timing.
It took 3 minutes. So basically, the water's passing through. I suppose since it's at
Okay.
level of the water is about right there or so. So when it's operating, the water level is about like that. So I guess there should be water in the box.
But that's why the screens at the back, So as long as the robot keeps moving forward, it not just stays here, water
Right,
goes
water.
into this one.
Okay.
So
And
no, water wouldn't be as
yeah, and it looks like it's positioned, well, I don't know how much it all weighs, but it's positioned roughly in the center of gravity there, kind of close. So it's not gonna, you have plenty of buoyancy, so it's not gonna be a problem, but, you know, you have to account for the additional mass of that light, of the water that's even flowing through there, right? As opposed to the dry weight. Good job, that's all, that's just like that, thanks.
Any other questions?
Yes. First, reintroduce myself. My name is Celestia Cho. I'm House of Health Subsystem in my 27th year. I don't deal with these types of robots. Robots I'm familiar with are on space delivery, so quite a bit different. But just to kind of echo one of the things that Jeff said, which I think is really important. It's just kind of where you put your requirements in your presentation. Because I immediately wrote on the very first slide, and I guess maybe a little twist. You broke things down right away into your subsystems. Usually you start with a very high level requirement. So you might think of your high level requirement as collecting algae, but you could also maybe when your high level requirement collect X amount of algae, per Y amount of operating time, which I think you broke down into your waste collection subsystem requirements. So usually you start with the high level system level requirements, and then from the system then you break into your subsystem, and then each subsystem you will have subsystem requirements, which is again what you said. Let's see. There is an educational outreach underwater robotics competition. There's a lot of resources there. I'm just curious, did you look at any of these resources in terms of components or sealing to keep them waterproof? They do a lot of things. And these are for completely submersible underwater robots.
Yeah. I think we looked into that. Kiani, her original idea was something that dealt with the competition. I don't know if it was that competition or something similar. And originally we were thinking, use it like a pelican box. Yeah. So, because they're watertight, sure, you all put electronics in and stuff like that. But then we looked at the price.
Yeah, pretty tight budget.
Yeah, I understand. All right. Let's see. Maybe you did this during prelim, but what about trade studies of your actual components? So, for example, battery based on power requirements, motor based on paddle wheel requirements. Did you do some trade studies for the types of components?
Yes, to an extent. For example, for the battery, we looked at several different types of lead acid batteries. We also looked at some other types of batteries, but it turned out lead acid was the cheaper kinds of batteries. So we went with lead acid, and then we kind of estimated roughly what we might draw amp-wise from all of our electronics. I think we estimated 2, I'm not sure. And based off of that, chose a battery essentially that was big enough to allow the robot to operate for more than 3 hours. I want to say it was 5 or something like that. And in the end, there was a battery available at the robotics lab. So, and it worked. It met our specifications still when it came to the power plant.
And then that's legit. So, let's see. So the software design you were unable to test because you couldn't get the program running, I guess, because of time limitations. Is that
Set creation.
yes.
And this was given a little bit of offsets, and before we couldn't start but the software by itself, like the modes that we
Your modes
presented,
operation, yes.
they work.
Okay.
But we couldn't test.
And that's what I was going to get at. If you were able to at least test or unit test your operating modes, even for fictitious simulated body just moving around, so that you're checking out your outer.
Yeah, we actually in prelim we did that exact
Okay.
thing. We did, and that, I could bring up the video.
No, I was just curious. That's fine. And I guess also during prelim, did you allocate like mass budget for each of your subsystems so that you could determine kind of an analytical center of mass for your system? Was that anything you did with prelim?
We didn't, but we knew what sensors and what electronics we needed, essentially. So we kind of based the physical design off of that, like how much money we have remaining.
It seems like, your operating height, to make sure that you're skimming the top of the water, that your buoyancy and everything, you've got to be pretty spot on in terms of where your vehicle sits on the surface of the water. So I think you mentioned that you were looking at tipping requirements and placing weight, but again, just making sure that everything sits exactly where you need it.
We did actually do some mass calculations where we were trying to estimate and see like how much volume of styrofoam we would need, but it wasn't really.
So basically what I did is, so I drew that model you saw in these slides, in SolidWorks, and basically cut it at a certain point. We knew the density of styrofoam. Then we kind of distributed everything in a way that it would level it out so the forces would be good. The design slightly changed a little bit, more and more. So basically, pretty sure.
Okay, just I think maybe one more. Let's see. So you've got roughly what's like that, maybe 3 inch by 4 inch opening here for your collection system. What happens if there's something floating in the way that strikes that opening? Floating driftwood or whatever it might be.
We had a couple.
It'll actually, I guess, be trapped right into it. So it's the whole idea of what Jeff mentioned here in terms of planning for contingencies. The thing of this is your mission, and your whole goal is to send this robotic vehicle out autonomously, and it's got to be able to account for any possible things that go on. So just trying to make you think about what are things that might come up. Floating piece of driftwood. Okay, well, it's great. I'm anxious to see this thing work. All right, that's it.
And I kind of echo what they say. It wasn't clear to me that we had requirements that were given to you, or the requirements were things that you laid out in order to do the project. So I wasn't sure if you had like system level requirement that then decomposed. I like the decomposition. You've broken out into each of the subcomponent levels, and that's a really good way to do that requirements analysis. I just wasn't sure if the requirements were on your own, or there were someone else's that you were trying to meet. You had a really good fallback on the cost solutions for the buckets, and that's something that would happen in a real world where you expect to get a part manufactured and it doesn't work out exactly right. So you start to look for a cost solution, because that can help you with cost and time and other things, budget, that you may not realize. So that was a really good way to go about solving some of your problems. Autonomous vehicle creation is extremely hard. And so you discovered that even though this is a mechanical class, you got bogged down in the electronics of this, because doing something where you have no control over it right off the bat is going to be difficult. It would be great if you could do like a crawl, walk, run kind of solution where you start with a remote control system, so you validate the mechanical design that you're trying to build. And I think you would have found that in the test that you did, you would come up with things like the driftwood or other ways, because it would have been really great for you to show that you were in the lake and you were doing collection, even if it wasn't autonomous, because that could be a spiral development down the line. So, you know, the fact that you manufactured the article and it's sitting here is really great to see. It would be great to see that you did some testing with it, because I think you were able to validate all of your requirements and the fact that you never really got to the lake. So, you guys did a great job. This is really hard work. Autonomous vehicle creation is not a simple task. And you found that out in all of the electronic board creation that you had to do. And so it's valuable lessons for you. Showing your data that you're collecting or any theoretical analysis that you could have done in a table form would have been great to put on the charts as well. The way that you presented, the fact that you have something here, you all had a piece of it that you certainly on is.
Any other questions?
I'll make one comment just to follow up. To give you an example with the space station, for example, crew members manually operate that thing and they have been for upwards of 13 years before they started to attempt to do the autonomous control from the ground using ground fence. So even in that point, then it's not fully autonomous, it's semi-autonomous. So I think your point about this crawl, walk, run, it would have been cool if you in RC control, you could fly the vehicle around or drive the boat around the vehicle on the vehicle like you do. That's the point.
So we do some autonomous one of our vehicles, and that's all I can tell you.
Can you go to slide 27? How did you collect this data?
Okay, so we actually did put the robot on hold. We didn't run the main program on part of the program. We simply told the motor to run full speed, and we collected GPS data, and we just collected GPS data, and from that, we created this plot in MATLAB. We converted the lat long to X and Y. Yeah, so how we got that line right there was just simply video.
So how did you retrieve the rover? Because I see the rover going in the middle of the lake and then it's going to be
Fishing line? Yeah, we had fish
Yeah, so
back into
we had a fishing line.
No, before we put it in the lake, we already had fishing line.
Yeah, sure.
So we just wrote a really small code that would just make it go forward for a certain amount of time. And it went forward and
Like mode one.
Yeah, pretty much. Actually, that's exactly.
But this is a very good example of unit testing. I mean, you want to do individual checkout of every single node and gradually get them.
You use the battery that you have, and that was great that you did that. The power output of a lead acid battery is different. You might have gotten like a micro battery or something different, right? Then you would have gotten radio motor control and maybe faster speeds. I don't know if you did any analysis to determine. It sounded like you ran the battery for some time on motor control with both paddles in the water. That's a great way to do that because you get the drive against the paddles. But in the end, you still said you had 1.25 volts of battery voltage. Did you determine what your ultimate life was using this particular battery, what your exhaustion was? Because you're going to need to know that so you can figure out how far is it out into the lake, and then what it's gonna take you to get back. And then the other piece that's missing would be when you're still above, yeah, it's the weather, you're still above.
Wind was a big problem.
Yes.
We tested it originally in dual, and it looked like it was going to work.
Yeah,
That's
at
a-
point
that's a
three,
good
4
image.
miles an hour,
That's
you
a-
have to have a completely calm day to
Just
help us.
and then going forward.
And then when we went to the lake, a couple of days, just after, just before it rained, and it was really windy. And it's,
I even asked them, are there motors going on around? Is it yet full speed?
Can you show the video on slide 67? Do you have also the video clip of the simulation of your software?
actually, it's all the same.
Subscribe.
Okay.
Please, everyone in this room had likes to be.
So, what's happened is really going really fast. We wanted to show it really quickly. So this white area is open water. Those red things are obstacles, and everything that's spinning really fast is the ultrasonic sensor scanning back and forth.
Which was going to be here.
So then this yellow area is the caution zone, and that gray area was the boundary border. So as you can see, I basically trapped it.
How do you help your to drop your GPS location when you start?
It stores primary sector matrix and also
Yeah, so shows
Loading flight 49.
on the original. So basically, yeah.
So you map the lake and you put in your matrix so you know where you are.
The robot does not have to make transaction calls and everything. It's just the same time, you just specify every single location on the map. Robot just based on its app, it knows how to move its steps on the
So it was interesting how we created these matrices. But basically, once we had it created, say the robot's right here, and maybe it's facing this way. So it reads this value off the matrix, and it's telling it essentially to point this way. In reality, it's a value from 0 to 7.
That's what your actually
Yeah, exactly. So then it would know it needs to go this way. It knows that basic controller to orientate itself like this. And then all the while it's going forward. So, and we've also tested it with the inaccuracy of the GPS, and it works really well. Same with that simulation that I just showed. That included the inaccuracy of the GPS.